All right, so the next thing that we're going to look at, which is going to take up sort of the rest of today's lecture, are the laws of logarithms, okay? And these are sort of an extension of those properties of logarithms that we saw before, okay? Um, and I'm going to write them down for you. There's three of them in this case. We're going to use them to solve and deal with a number of different problems, okay? So we have this sort of preceding statement, right? So a is greater than 0 and a is not equal to 1, right? Setting up a to be our base. And then let's say let capital A, capital B, and capital C be real numbers. I guess I'll just squeeze this in at the end, where A and B are positive, right? And here are our three rules, okay? We'll say number one, we have log base A of A times B, right? That's equal to log base A of A plus log base A of B, right? What's an important note here is that this log of A plus B equals log of A plus log of B. This is not true, okay? We cannot do this. There are specific values of A and B where this is possible, but as a general rule, that's not true, okay? Number two, this is, in a sense, a special case of the above one, right? A divided by B. That's log base A of A minus log base A of B, right? Because remember, this is just B to the negative 1, okay? And then our third one, okay, let's say we have log base A of A to the C, okay? And the nice thing about logarithms and how they handle these exponentials in here, right, is that even if, this big A is different than this small a, what we can do is we can pull out this C and get C log A of A, right? These exponentials, when they're in the argument, can always be sort of brought out front, okay? And this allows us to evaluate things that might not be exactly obvious right from the get-go, okay? Let's say evaluate the following, okay? Let's look at this first one. Let's say log base 4 of 2 plus log base 4 of 32, okay? So notice 4 is not a factor in either of these, right? But what I can do is I can use this rule, right, to write this as log base 4 of 2 times 32, right, which is log base 4 of 64. But 64 is 4 cubed, right? So since we're taking the log base 4 of 4 cubed, that just leaves 3, okay? Let's do one more of these evaluation ones. Let's say log base 2 of 80 minus log base 2 of 5, right? Once again, we're kind of stuck with evaluating each of these in turn, right? We would not be able to get an exact answer. But because we're subtracting, what we can do is we can take log base 2 of 80 divided by 5, right? And this is equal to the log base 2. Well, 80 divided by 5 is 16, right? And 2 to the 4 equals 16, so our final output is 4. Now we can look at another class of examples, okay? And that's the class of expanding. So we're going to expand the following expressions. And this is basically asking us to, get this single statement, right? Say the log base 5 of x cubed y to the sixth, right? And we're trying to expand this as much as possible, right, using our log laws. Well, I have the product of two things in here, right? So I can split that up into log base 5 of x cubed and log base 5 of y to the sixth, right? And then I can use that there are exponents right here and sort of fling them out front to get 3 times the log base 5 of x plus 6 times the log base 5 of y, okay? And that's as expanded as this guy can get, okay? So one more like this. Let's look at the natural log of, say, ab over the cube root of c, okay? First thing that I can do is I can expand that division, right? So it's the natural log of AB minus the natural log of the cube root of C, right? But the cube root of C, note, right? The cube root of C is C to the 1/3. So I can take that 1/3 and I can move it out, right? And additionally, I can expand out this product, right, into natural log of A plus natural log of B minus 1/3 times the natural log of C, okay? We can also sort of go in reverse, right? We can say combine into a single expression. We'll just do one of these. Let's say we're looking at 3 times the natural log of s plus 1/2 times the natural log of t minus 4 times the natural log of t squared plus 1, okay? So the first thing that we'll do is we'll take all of these front-facing coefficients and make them into exponents, right? So that's going to be the natural log of s cubed plus the natural log of the square root of t minus the natural log of t squared plus 1 to the 4th, okay? And then these two are going to be a product, right? So we can go the natural log of s cubed times the square root of t minus the natural log of t squared plus 1 to the 4th. And then because we have this subtraction here, we're going to divide this guy by that guy. We'll get the natural log of s cubed times the square root of t over t squared plus 1 to the 4th, and I'll put that whole guy in brackets. Next up is an example with something called the law of forgetting. And the law of forgetting deals with a number of things, okay? So it looks at how your performance in a skill degrades over time, okay? And it looks like this. Log P equals log P naught minus C times the log of T plus 1, right? Where P naught is sort of like your initial score, right? Like how well you learned something, right? C is some sort of constant, right? Dependent on the task. T is your time in months. And then this P without the subscript, right, is sort of your output, right? Your performance after T months, right? And so what we want to do in this situation is see if we can solve for p, right? Doing some algebraic manipulation to kind of isolate p, right? Because right now it's in a log, right? And here's how we want to think of it, right? Because our logarithm function is 1 to 1, this is the case. If log of x1 equals log of x2, well, that means that x1 equals x2, right? This isn't true with the general function, but the log is 1 to 1, so we can utilize this, right? So we have log of p on this side, and we want to isolate log of something over there. So let's do that a step at a time, right? We have log of p. Well, we have log of p naught minus, what if I move that constant up, right? T plus 1 to whatever my constant is. But that would mean that we're subtracting the log of two expressions, so we can take the log of dividing one by the other, right? And now we have what we want, right? We have log of p on this side, and we have log of stuff on the other. And because the logarithm is 1 to 1, I can essentially cancel those logs. And that gives me that p is p naught times t plus 1 to the c, okay? And you could, plug this in and sort of be like, hey, if you score 90% on a test, right, and you have, some given value for c, what should you expect your score to be after 2 months, after a year, after 10 years, right? This kind of will give you an idea for the speed at which your knowledge of a thing degrades. One last thing to cover today, that's a thing called the change of base formula, okay? And it asks the following question, okay? So say we have, we know the log base a of some undetermined value x, okay? But we want to know the log base b of x, okay? Here's how we're going to do this, okay? Let's set, y equal to the thing we want to know, right? Log base b of x, okay? And I'm going to walk you through this derivation, which is known as the change of base formula, right? Kind of what pops out the other side. But we know that, we have this form as a logarithm here, but we can write it in this exponential form, right? B to the y equals x, okay? So we're going to start with this, right? We're going to start that b to the y equals x, okay? Now we're going to take log base a of both sides, okay? So we have log base a of b to the y equals log base a of x, which is great, right? Because that's what I have, right? I guess I didn't write that. So say we know that, okay? But then what can we do here, right? Let's, move that exponent down. So we have log base a of b equals log base a of x, okay? But I know that y is equal to the thing that I want, right? So I want to try and isolate it. So that would tell me that the y, the thing that I want, is log base a of x over log base a of b, okay? And this is the change of base formula. Right? This is how you can take take a logarithm in one base and transform it into the language of another base, right? We have, say, the log base b of x is log base a of x divided by log base a of b. Isn't that nifty? Okay. And one of the reasons where this is very useful is when you're trying to use a calculator to evaluate these logarithms. Now, a calculator isn't required in this class, but there are times where it's useful, right? And so, for example, let's say you want to calculate log base 8 of 5. Now, the problem is most calculators only have two log buttons, right? They have log base 10 and they have the natural log. They don't have a log base 8, okay? But this is why we want to use the change of base formula, right? We'll sort of write it again here in the corner. We'll say log base b of x, what's that equal to? Well, it's log base a of x over log base a of b, okay? And in this situation, what do we have? X is equal to 5, right? Our base in the original one is equal to 8. And our new base a, well, what do I want our new base to be? Well, we could go e, or we could go 10, right? It's sort of up to us. Let's start with 10, okay? And the beautiful thing is it's going to output the same no matter what your choice for a is, okay? But let's work this out, right? We have log base 8 of 5. That's going to be log base 10 of 5 divided by log base 10 of 8, okay? And if you were to punch this into your calculator, right, and now that we have log this in the language of log base 10, we can. If you put that in your calculator, you're going to get about 0.774, okay? One more of these. Let's say we're looking at log base 9 of 20, okay? In this instance, the thing we're looking for the logarithm of, our x, well, that's 20. Our original base is 9, and in this case, let's let our new base be e, right? Because our calculators often have a natural log thing as well, okay? So let's work this out. We have log base 9 of 20, right? That's going to be the log in my new base of the value I'm looking for, in this case 20, divided by the log in my new base of our old base, right? Thankfully, we have a little bit nicer language for these natural logs. So ln of 20 divided by ln of 9, right? And that's going to give you about 1.363 if you were to punch that into a calculator. Again, you could totally put this in the language of the common log and get your answer, right? You could do log base pi here for your value of a, and you would always get this answer.